we're going to discuss today about spontaneous changes, about entropy over the second law. So let me start with the second law itself. Yeah, and you know that if you can't hear me at the back, just raise your hands, everybody. I don't know, something's going wrong with this mic. Okay, so the second law itself, as you know, is that the entropy of an isolated system keeps on increasing, right? That is, delta S total is greater than 0. This is what you've learned, right? Or in other words, you say that the entropy of the universe keeps on increasing. What is entropy? Essentially randomness. And how do you measure this?
We define the entropy of a crystalline substance at 0 Kelvin.
Okay, a pure crystalline substance at 0 Kelvin is defined as 0, correct? But we've not yet come down to 0 Kelvin, so we'll talk about this later. But normally what you say, if you wish to measure entropy, what you say is whatever the heat has been exchanged at a given temperature, right? So you say that ds is equal to dq in a reversible fashion, okay? That's very important, dq reversible by t, right? Well, what essentially work, there are two ways you can exchange energy, right? Either by doing work or by heating up or cooling down the system. If you do work, you think of work. Work is like you're pushing this piston. You're always pushing it in a certain direction. You know, your gas atoms could be moving very randomly. On an average, they don't move at all, the total sum. And if I push this piston down, still they don't move at all. The random motion is exactly cancelled as it was before. And what I have done is to push them down. I have not introduced any randomness. I have actually given it a direction. So whenever you are doing work, you cannot increase or decrease the entropy of the system. Yeah? I can't, because except against vacuum. Irreversible cases are different. We go down, always the work is trying to push the atoms in that direction. Yes? So I am not gaining or losing any entropy. Maybe it's just pushing out. Now, if I heat up the system, then these atoms could move about randomly in any direction. So heat is the one that essentially generates all the randomness. That's the random motion. And the reason you divide by t, well, one obvious reason is that of course you want a state function, so you get it by dividing by t. But the reason is fairly simple to understand. What you want as a state function is the percentage the percentage of entropy that has increased or decreased. And think of the system at 0 Kelvin. As I said, at 0 Kelvin you have pure crystalline substance. It does not have any entropy. The moment I supply some amount of heat to it, the entropy of the system, the randomness of the system increases infinitely. The percentage increases infinitely. But if I do the same thing at room temperature, the percentage increases not infinite. Yes? So to do that kind of normalization, so as to say, we divide it by temperature so that we get to know exactly what is the amount of increase of randomness at that given temperature. Okay? So this reversible part is very important, one thing. And that is, if I don't write anything, mostly I'll mean that it is for the system. If I write something over here, then I would rather write surrounding, which would be equal to dq by T surrounding. Okay, dq surrounding by T surrounding, and what would be dq surrounding would depend on the situation, of course. If it's an adiabatic change, it's going to be 0. If it's a reversible change, it's just going to be the exchange of heat. Okay, but T surrounding is something which you can assume it to be a constant, because normally the surrounding is assumed to be a very large one. So if I take an infinitesimally small amount of heat out of the surrounding, it's not going to change the temperature of the surrounding. The system, on the other hand, is a small one. Yeah? Okay. So with those kind of definitions, let's say, try to define the statements of the second law. Okay. Now, what I'm going to do is finally connect the mathematics with these kind of experiments. So, one statement of the second law is that it is impossible for any system to operate in a cycle. Very important, in a cycle. So let's make that cycle. This is a cycle, some direction of the cycle. It's impossible for any system to operate in a cycle that takes heat from a hot reservoir. So temperature H, it's a hot reservoir, and the meaning of reservoir is that it's large enough. If it gives heat, its temperature does not change. And produce some work. Okay, so in a cycle, it's impossible for any system to operate in a cycle that takes heat from a hot reservoir and converts it into work without into work in the surroundings, without at the same time transferring some heat to a cold reservoir. So it must transfer, so this is the heat that it has taken up from the hot reservoir. It must transfer some heat to the cold reservoir. Okay. So, if this part was not there, it's not possible. That's what the statement says. The first law actually says that this part is not required. It says conservation of energy. I bring in heat to the system, it converts into work. This part says no. If I bring in about 20 units of this heat and 10 units or 12 units are taken up as work, then 8 units have to be lost. I cannot convert the entire amount of energy from one form to the other. An alternative statement. So this is Kelvin's statement, okay? And if you can think about it, it's an engine. An engine takes up heat. You heat up steam. It takes the heat, does the work, rotates this crankshaft, whatever it is, makes the train move, and just junks away some of that heat into a cold reservoir. So this is an engine. And the statement that I just mentioned, and you need not write it down because it's all here in print on the web. So the other statement is by Clausius. And let's see if you recognize what kind of a device would this be. A refrigerator, of course. What it says is, it is impossible for any system to operate in a cycle that takes heat from a cold reservoir. So cold reservoir, it takes up heat. We work in this cycle and transfers it to a hot reservoir. Like that, without at the same time converting some work into heat. Some work has to go in. Yeah, so I cannot have any 100% efficient refrigerators either. There are many more alternative statements, but let's not worry about them. What one sometimes hears about these things is that, you don't have an AC, okay, buy a refrigerator, put it in your room and cool your room. Now if you know this kind of a law, what do you expect will happen? The room will heat up, yeah? So you need to push in some work before you can actually cool down. And the moment you put it in, you're actually pumping more energy than what you're gaining out, right? So whatever the sum, so there will be some heat extracted plus some work that needs to be done on the system, and this plus this would be equal to QH. I didn't write that part. So you'd rather not be able to do that thing. Okay. So now this is the picture that you get out of your engines, your refrigerator, your devices. But you also want to connect it to entropy. It clearly shows second law. No problems with that. It shows that I cannot convert everything from, I cannot convert the entire energy into work. I need to lose some energy. I will lose some energy. But then how do I connect it with entropy? And if you wish to connect this with entropy, first what you need to show is that entropy is a state function. That's fairly easy. Let's say what I need to show is integral of ds over a cycle is equal to integral of dq reversible by t is equal to 0. That's what I wish to show. So what I'll do is, I'll do this in 3 steps. In the first step, I'll construct something called a Carnot cycle and use the ideal gas as the working gas. So Carnot cycle with ideal gas. So let me draw this Carnot cycle correctly. So pressure, volume. So I start from one point, I have to end at the same point. So the Carnot cycle, which was designed by Charles Carnot, a French engineer, goes like that. An isothermal expansion from A to B, another adiabatic expansion from B to C, an isothermal compression from C to D, and back an adiabatic compression from D to A. Okay, so this and this are the isotherms, and maybe another one, and this two are adiabats. And now I have a hot temperature over here, TH, and I have a cold temperature at the lower isotherm. When I go through the adiabat, my temperature changes from the hot to the cold one. Okay, so what I need to worry about then is to worry about the changes in the entropy